Hello, welcome back. So in this session is about the model evaluation. So we'll see like what are we discussed till now about the F1 score or AUC. We'll see how we can actually implement that using the SageMaker. So first let's start at the basics. What do we mean by model evaluation? In simple term, model evaluation tells us how good our model really is. It's a process of testing a trained ML model on a new unseen data to see how it performs. We don't just care about whether it performs well on training data. That's not useful in real world scenarios. We want to know, is a model actually learning something useful? Will it work on future data it hasn't seen before? To do that, we split our data, train on one part, test on another. So and compute metrics that tell us how close predictions are to the truth. So in essence, model evaluation is a reality check of machine learning. So why model evaluation is important? That one of the reason is just give answer this question. Imagine you're hiring someone and you are testing them, right? You want to make sure that you test them on whether they can answer some real world scenarios, real world job tasks. So model evaluations are exactly that role for machine learning. It checks generalization. Will the model work well on the real world data? It helps you choose the right model. You might try logistic regression, XGBoost, or random forest, but without evaluation, you are just guessing. It also helps you to monitor model over time. If your model performance drops after a deployment, evaluation metrics can flag it early. And perhaps most importantly, in high-stake domains like healthcare, finance, or security, evaluation makes sure that the model is not just accurate, but also trustworthy and aligned with your business goals. Now we'll see some metrics that helps us to give an idea of how well the model is performing. So the first metrics we talk about is precision. One of the most important evaluation metrics in classification, especially when false positive matter. So imagine you're designing a spam filter. If your model predicts that an email is a spam, but it's actually not, that's a false positive. And it could mean a user misses an important email. So precision helps us to measure how often our positive predictions are actually correct. So if your model predicts 100 emails as spam and only 80 of those are actually spam, your precision is 80%. So it tells you when I say it's spam, how often I'm right. So high precision is critical in fraud detection. You don't want to falsely flag normal transaction and block the customer cards and unnecessarily causing trouble to the customer. In medical diagnosis, you don't want to wrongly tell someone they have a disease. So remember, precision is about the quality of your positive prediction. Now let's look at the recall, which is all about the coverage. How many of the real positive cases did our model actually find? So going back to spam detection example, say there are 120 spam emails. Your model finds 80 but misses 40. That's a recall of 67%, meaning it missed 1/3 of all spam messages. That's not great because missing a spam might let phishing emails slip through. And in other domains like medical diagnosis, missing a positive case can be delayed treatment. And a fraud detection, missing a fraud could be a financial loss. So if you care more about not missing any positives, recall user metrics. So for example, think like if you are doing a medical diagnosis, you don't want to miss the positive. That means if the patient has a disease and you say he doesn't have, that is a negative, then that is not a good thing. But if the patient is doesn't have a disease, but you flag the patient has a disease, that is still okay because doctors can do a follow-up check and determine that yeah, this patient doesn't have the disease. But not flagging is a challenge because it will go undetected. So in case of medical diagnosis, maybe recall is more important than precision. So in contrast to precision, which asks when I say yes, how often I am right. So but both are important. So we'll bring them together soon when we discuss about the F1 score, the harmonic mean of precision and recall. Now that we covered precision and recall, let's talk about F1 score, which bring them together into a single number. So why do we need this? Because sometimes you face a trade-off. If you push her for higher recall, precision may drop. If you tighten precision, you might miss real positive. So it's like you want to balance. You don't want to, just because you want to detect all the spam emails, you cannot classify some genuine emails also as spam. Just because you doesn't want to miss the negatives, you cannot, flag every patient has got a disease. It has got unnecessary, follow-up checkups and then medical expenses and everything. That's one of the reason F1 score gives you a way to balance the two using the harmonic mean, which punishes extreme values more than a regular average. So let's reuse our spam filter example. We have a precision of 80% and recall of 67%. So your F1 score is 73%. This gives you a holistic view of your model performance, especially in imbalanced data set like fraud or rare diseases, when both false positives and false negatives carry cost. So to summarize, F1 score is a great overall effectiveness metric when neither precision or recall can be ignored. Next up is AUC, short for area under the curve. This is the most powerful metrics when your model produces probabilities, not just hard labels. So the ROC curve plots true positive rate versus false positive rate, right? It tells how well the model can separate the classes across thresholds. So if AUC is 1, you have a perfect classifier. If it is 0.5, it is almost like just like flipping a coin. So it is less than 0.5, you are actively making wrong choices. So what's powerful about AUC is that it's threshold independent. It looks at all possible classification cutoff and say on average how well can this model rank a random positive higher than a random negative. So for example, in credit scoring, AUC shows how confidently your model can prioritize risky customer. In healthcare, AUC shows whether the sick patients are ranked above healthy ones in probability. So while precision and recall depends on specific threshold, AUC is more holistic, especially useful during a model selection. So now let's talk about one of the most useful diagnostic tool in classification, the confusion matrix. Rather than just looking at a single number like accuracy or precision, a confusion matrix shows you all outcomes of a binary classifier. It tells you true positives, that is model correctly predicted positive, false positive, model predicted positive but it was actually negative, false negative, model predicted negative but actually positive, true negative, model correctly predicted negative. So this breakdowns is critical because a model with 95% accuracy might still be missing all the rare but important positive cases. And you wouldn't know unless you looked at the matrix. So in case of say for example in medical diagnostics, false negatives can be life threatening. In fraud detection, false positives can cause user frustration. The confusion matrix shows where the model struggles and what kind of errors are most common. So you can improve on it very precisely. Now let's shift our focus from metrics to understanding the model. This is where model explainability becomes critical. So far we have focused on how accurate or how precise a model is. But what if stakeholders or a regulator ask, why did this model make the decision? So you are having some loan approval ML algorithm which is rejecting or approving a loan for a customer. But the customer might want to know why a loan being denied for a particular customer, right? We should be able to explain why the model made a certain decision. So there are two kinds of explainability. One is called global explainability, tells us which features the model generally relies on. For example, income might be more important than location in predicting credit risk. So it tells an overall what features model is using to make a decision is what in a global explainability. Local means tell us why specific prediction was made. For example, why the person got flagged for fraud, why this person a credit application is being denied. So explainability isn't just a nice to have, it is requirement in regular domains like finance or healthcare or employment. So the key takeaway is that a high performing model that can't be explained is a risky. So explainability bridges the gap between model performance and the human trust. And lot of times this is also a requirement for a regulation requirements. So let's discuss about one of the most widely used explainability tool called SHARP. SHARP stand for sharply additive explanation, and it based on cooperative game theory, specifically the concept of Shapley values. Think of each feature in your data set as a player in one game trying to influence the outcome. So the SHARP calculates how much each feature contributes to the final prediction, just like how you might split prize money based on each player contribution. So what makes this powerful? It gives exact, attribution for each feature. It works across many types of models, from XGBoost to deep learning. It can explain why a prediction was made and how your model behaves overall. So if your model predicts that a transaction has a 92% chance of being fraud, SHARP might shows that high transaction amount added 0.4%, or transaction time added 0.3%, new device added 0.2%. Then it lets you say here exactly why model said it's likely fraud. This level of transparency is crucial in making ML model auditable, trustworthy, and aligned with the human judgment. Now let's talk about how we actually put this explainability into practice, especially in production grade systems. So we have a service called SageMaker Clarify in AWS. Is a native tool for handling bias and explainability in ML models. It covers two key problems: bias both in data and in model outputs. Explainability using a SHARP to break down prediction. So for example, before you can train your model, Clarify can tell whether your feature like gender or location are dominating your data set. After training, Clarify can evaluate if the model treats different groups differently. For instance, all female applicants denied loan more often, whether that particular feature has got more impact. And then it uses SHARP values to show why specific prediction was made, feature by feature. So you can run Clarify as part of your SageMaker pipeline also, and to generate the bias reports or explainability reports. And a full model governance artifact that you can use for all your compliance and stakeholder reporting. So this has become increasingly important as more industries face AI regulation. Clarify help you to build the model that are not just powerful but also fair, transparent, and accountable. So now let's open our Jupyter notebook and then run some evaluation on the day and on our model. So again, as I told, the data for this this code is available already in this GitHub repo. I'm pretty much using the same repo with minor modifications, based on my data. But otherwise, you can use the same repo and the same code for running this evaluation also. So here again, we are doing all the imports, and then I'm restoring all the values, the bucket, everything is stored in the memory again. So I'm loading my model, which I have trained initially, and then once I load the model, we are using test.csv or test CSV file for doing the evaluation, because this is a file the model hasn't seen during the training phase. So now this is a new data for the model. Now we can see how the model actually predicts with the new unseen data. So that's what we do here. After reading test.csv, we construct a D matrix and then we run the XGBoost. We run this predict function call on the method on this model with this data. Now we print the accuracy and the AUC score for this. We can also print F1 or recall here. Now this would give us an idea like how well my model is performing, right? I can also generate the classification report and then store the report in in an S3 bucket. And after this, I am also doing the converting this into a reusable code, so that in future, if you want to build a SageMaker pipeline to run this model end to end, that right from the data preparation to all the model feature engineering or model training, registering, deployment, evaluation, everything you want to build a SageMaker pipeline, having a reusable code makes it easier for you, right? So the next important part, maybe I want to spend more time on the SageMaker Clarify part. So here we are using, as we told, we are using SageMaker Clarify to explain the model predictions. So one important concept here, when we actually say SageMaker Clarify is the baseline data. So this is a type of a reference point that Sharp uses to calculate how much each feature influences the model output. So you can see that in this code snippet here, where we are building Sharp config, we are passing the first row as a baseline data. This baseline is being set to first row of our data set, essentially one customer data. Then Sharp will ask, if you know nothing except this baseline customer, what would the model predict? Then for each other record, it measures how much each feature shifts the prediction away from the baseline. So the baseline customer has a voicemail, made 2 customer service calls, and stayed with the company for 120 days. Sharp treats this as a neutral reference. Any deviation from this, like a different number of service calls or not having a voicemail, is evaluated in terms of how it changes the model prediction. So it is important to note that the first row is convenient but not always ideal. In practice, we might want to use a more representative baseline, such as an average customer, or even provide multiple baselines to improve the accuracy, especially when using the Sharp analysis. So now, after having all these things, other important thing is that we are having model configs. What SageMaker Clarify will do is it will spin off a model at runtime, so that you don't have to disturb the production traffic. And then once you are done with that model clarification, it tears down the model. That's what the model config being used here. And then once we have this one, we are having clarified data config, we pass everything, we give a name for that, and then we run our explainability run. So then once you give it, it actually runs the explainability, it takes some time to explainability, and then after running everything, it generates the report. So once it generates a report in a S3 bucket, so we can go back to the S3 bucket here. In the XGBoost, there is a folder called Clarify Explainability, and then it has generates a report in both PDF file and HTML and the JSON also. Now let's open the Sharp report and see how our Sharp report looks. Right, this is our Sharp report, which is analysis report. It tells how many features being used. So what is the Sharp analysis being done? It is displaying for each label, it displays top 10 features with the greatest feature attribution. So what it means here is that if we see vplan is equal to yes 0.04. So what it means is that this Sharp value, this feature alone, on average, contribute to 0.04 units for the churn prediction. Or another way to put this is that the Sharp value of 0.04 means that the feature changes the model output or score by 0.04 units, an average across all samples. So if your model is outputting probabilities, this 0.04 is a probability units. So voicemail plan S, basically what it means is that it impacts the predicted churn probability by about roughly by say a 4% on average, right? That's what it means. Now it tells you what all other features are also contributing to this particular prediction by the model. These are all the top 10 features which actually impacts. Now I get to know what features are important, then whenever I'm getting whether the customer churn yes or no, then I have clear indication. Even if I'm building a credit card denial for a customer, the model deny, then I know which feature, maybe is it a income, or it is a past credit history, or maybe the current credit history. It could have a lot of features available for the model. It can tell which feature actually impacted your model, right? So this is about the model evaluation. So far we have pre-processed the data, we have trained the model, we have evaluated, we ran the SageMaker Clarify report to explain why prediction is made. Our next job is to deploy this model and then create an endpoint and then execute that model by passing a data which the model hasn't seen before.